Okay, hello everyone. Welcome to my aerosol instrumentation class. So this time we're going to review some important concepts on single particle dynamics. So some of these concepts are actually quite important when we are trying to design systems to sample and also to measure the aerosols. Okay. So before we do that, let's do a quick recap of our last class. So last class, we talked about the definition of aerosols. So basically, the aerosols are suspensions of liquid or solid particles in the air. And then these aerosols can make an impact onto our environment, which include the air quality, human health, and also our Earth's climate. And through the climate effects, we further divide it into the direct effect, which is about the scattering of the solar radiation, and also the indirect effect, where these aerosols form clouds and further reflect the radiation back to the universe. So we further discussed that these impacts are actually a result of the properties of the aerosols, and these properties can be categorized into physical, chemical, and biological properties. And we need to use different instruments and design different sampling systems to characterize these different types of properties. So before we introduce these more detailed instruments to do these sophisticated measurements, or sometimes they can be pretty simple, we have to first understand how the aerosols are being transported. Okay, so this is related to the single particle dynamics. So if you have taken classes on air pollution or aerosol mechanics or aerosol science and technology, you probably have already gone through some of these fundamental concepts. So it turns out that these are quite important knowledge for our aerosol instrumentation class. So that's why I want to do a review of these concepts. So we're on the same pace, right? So later on when we talk about different sampling systems, we know the concepts over there. So one simple example of how these aerosol dynamics might influence our measurements or influence your projects is I believe that in the future, if you need to sample the aerosols directly into an instrument, then you need to design a sampling or a tubing system that actually extract these aerosols and further introduce them into the instrument, right? And then you need to find the right tubes or to design the right passage of the aerosols in your system. But if you go to the market, you can see that there are so many different types of tubes, right? You can have the stainless steel ones, you can have the copper ones, you can have the plastic ones, and then there are also the Tygon and then the nylon and all different types of tubing, and they can have different types of fittings as well. But which type of tubing should we use for your specific task, right? So in our lab, we also, or in the aerosol field, people also use the black silicon conductive tubing because they're very flexible, but can you use it in some of these organic aerosol measurements? It turns out not, right? Because they can outgas and generate a lot of derivatives from the surface of the tubing material. And then there are also pros and cons for different types of these tubing, and they're related to the aerosol transport within these tubings. Okay, so after this class, you are going to get the fundamental concepts about the aerosol transport or aerosol dynamics. So when we discuss these criteria or methods for particle sampling or particle measurements, you will get an understanding of what we're dealing with. Okay. So to talk about the aerosol dynamics, we first need to understand what are the different types of forces that can be applied onto a particle. Okay. So if you think about these different types of forces, I can probably list a few of them, right? So they can include gravity, right? So gravity can be represented as mg, right? Further, we know that the mass can be calculated by volume multiplied by the density of the particle, right, and g. And then further, we can assume that all of these particles are spherical. So you can calculate the volume based on pi over 6 dp to the third rho pg, right? And this is basically the gravitational force. So similarly, I mean, particles can settle down due to gravity, but they can also rise up, right? That's because of buoyancy, right? So Fb is going to have the same equation compared to the gravitational force, except that here the density term should be the fluid density, I should note that here the dp is just a particle diameter of particle. And here specifically we assume that they are spherical. Particles are spherical. Okay, so rho p here is the particle density. Okay, rho f is the fluid density. Okay, so another example can be the electrostatic force. Okay, so sometimes people will use electrostatic force to separate the particles. So one of the most widely used instruments to monitor aerosol size distribution, what we call the scanning mobility particle sizer, actually use the electrostatic force. Right? It lets the particles to move within an electric field, and then because of the mobility, different mobility or different size of the particles, they can be separated out. So under the electrostatic force or the electric field, then the electrostatic force can be represented as Q multiplied by E, right? So the Q is the charge or the charges on particle, and then the E on the particle, and E is the electric field strength. Okay, so there can also be thermophoretic force. Okay, so basically if you have a particle that's in a temperature field, you have a hot side, you have a cold side, so the air that's surrounding the particle are going to have different kinetic energy, right? They're going to have different speed. And then the particles, basically the air molecules are going to also collide with the particle, right? It's like tiny balls that are bombarding the larger particle here, okay? And then because the hotter side, the aerosols or the gas molecules have a higher speed, higher kinetic energy, higher momentum, so they're going to give this particle a net movement towards the colder side. So there's a force that can describe the the equation that can describe the thermophoretic force. Okay, so we can also list, let's say, the magnetic force, and so on. Okay, but if you look at all of these forces, they're actually generated by an external field. So they can drive the movement of a particle, or they can lead to the movement of a particle, if the particle initially was stagnant, right? If it's stagnant. But there's also an intrinsic field that tries to limit the movement of the particle. Okay, so basically a force that can constrain the relative movement of a particle within the field, or with the relative movement of particles against the flow. And we call that force as a drag force. Okay. So the drag force, it is actually very common in our daily life. Okay, so you may think drag force of, let's say, have anyone of you been to skydiving? Or I haven't been there, but if you just watch the movie or watch the on TV, so basically when people jump off the plane, they're going to move downwards because of gravity, but there's also a strong wind that's blowing them up, right? So they're not moving upwards, but there's a force that tries to balance the gravity. So you may think that the drag force may be a very tiny force compared to the gravity, but actually it can be a very important force that can balance the whole entire movement of the falling object, that can strongly constrain the movement, constrain the velocity of this particle or of this object. Okay, so we can give a simple example calculation, right? So, I mean, in Miami, it rains a lot, right? And then we have rain because we have rain droplets up in the sky, in the cloud level. So we can calculate the velocity of a rain droplet, let's say, assuming that there's no drag force. Okay, so we can find out what the velocity should be, or what the velocity might be if there's no effect of the drag force. So what we can do is you can first assume a certain height of this raining cloud or precipitating cloud, which is around, let's say, 2 kilometers above the ground. Okay, so we know that there are tiny rain droplets. Okay, so because of gravity, they're going to move downwards because they're too heavy. So assuming that there's no force that's balancing the gravity, right? So what's going to happen is that according to the Newton's second law, you're going to have m dv dt equals mg, right? The acceleration multiplied by the mass should equal to the external force added onto the particle. Okay, so you're going to have v dv dt equals g. So since the initial particle velocity is just 0, so you're going to have v equals gt. Okay, so you also know that while the particles are accelerating, okay, it has a total distance to settle right? So the total distance is 2 kilometers. So you can integrate the velocity. So basically integrate velocity by time. And then this should equals 2,000 meters. Okay, so you're going to have 1 over 2 gt squared equals 2,000. And then further, if you assume that g is 10 meter per second squared, right? So you're going to have, let's say, gt squared equals 4,000, and then t squared equals 400, and then t is just square root of 400. That's 20 seconds. Okay, so then you know the total time for the particle to settle down. Then what about the final velocity, right? The final velocity is just g multiplied by t. That is 10 multiplied by 20 seconds, which is 200 meters per second. So is this a fast speed, right? Is this reasonable in terms of the rain falling speed? Okay, so just as a comparison, okay, so in the early days when people are trying to make the ammunition, right, like a pistol, so for example, when people first find out explosives to set up the guns, right, the bullet speed is around 100 meters per second. Okay, so nowadays the bullet speed can go to, let's say, 400 all the way to 1 kilometer per second. That is very fast. But even at that time, this speed is very, I would say it's very significant, right? Because let's say the speed of sound is around 300 meters per second. Okay, so basically, if there's no drag force, it's going to be like raining bullets from the sky, right? And sometimes the rain droplet can be pretty big as well. Okay, so it turns out that if you measure the velocity of the falling rain droplets, they're generally in the range of around 10 meters per second. Okay, so you can see the direct difference if there's drag force and if there's no drag force, right? If there's no drag force, I don't think there will be living organisms on our Earth, right? Because the momentum or the kinetic energy of the rain droplets will be so big. So so basically this is how drag force can influence our daily life. Okay, so but then how do we calculate drag force? So people have been thinking about this calculation for a long time, and I would say the first equation to describe drag force is according to the Newton's law. Okay, so it's in the year of around 1680, right? Newton was really busy during that time setting up all the new equations. So in his equation, so the drag force is described as 1 over 2 rho F VR squared AP and CD. Okay, so let's look at the terms one by one. So rho F here, this is the fluid density. Okay, VR is the relative velocity. Okay, it's the relative velocity of the or between the particle and fluid. Okay, so AP is the cross-section area, and then CD is what they call the drag coefficient. Okay, so the drag coefficient is not a constant. I would say. Okay, so it's just at that time, in certain flow regime, people find out that the drag coefficient is somewhat similar to a constant, but in other flow regimes, it is not. Okay, so we can also take a look at the unit of these different terms. Okay, so the fluid density is going to carry a unit of kilogram per meter cubed, and then the relative velocity is, let's just write it out here. Relative velocity is meter per second, right? So you're going to have meter squared per second squared. Second squared. And then AP is a cross-section area, so another meter squared. And then the drag coefficient is unitless, right? So how does this relate to force? Okay, so we know that the force is basically, if you think about the gravity, right, the force in the unit of Newton is equal to the mass, kilogram, multiplied by the acceleration, that is meter per square second. Okay, so this is how we describe or how we define the unit of the force, that's Newton. Okay, so you can see that we can cancel some of the terms here, right? So this is cubic meter per cubic meter, right? So you can cancel two of them here, one of them here. So it's directly kilogram per second square, and then kilogram meter per second square. This is going to carry a unit of Newton, right? Okay, so according to Newton's law, at least in terms of the unit, it works. Okay, so if we further look at this equation, they also make sense physically, right? So first, you can find that the drag force is proportional to the fluid density. So if you pull a ball in the air and try to pull the same ball in the water, right, horizontally, then you definitely experience different drag force. In the water, it's going to be higher, right? The drag force is going to be larger. So this kind of makes sense, right? At least they're positively correlated. And then the drag force is also proportional to the relative velocity squared. We probably will have question or have difficulty understanding the square term here, but at least the higher the velocity, the larger the drag force. It is showing that. Okay, so the drag force is also proportional to the cross-section area. This makes sense too. If you're trying to pull a needle and then try to pull a spherical ball that has the same mass of the needle, right? So the drag force on the ball is going to be larger compared to the needle, right? Because the needle will have a smaller cross-section area. Okay, so I would say that these different factors, they indeed make sense at that time, right? At least if we travel back to that time, if Newton showed this equation in front of us, we won't go against it. Okay, so then finally, this is a drag force. So it turns out that finally is a drag coefficient. So it turns out the drag coefficient is a function of the Reynolds number. Okay, so when the Reynolds number is smaller than 1, basically what people call the creeping flow. Okay, so the Reynolds number is going to have a specific form. So it was around 200 years later that people find out actually under this laminar creeping flow condition, we're going to have a more elegant way of showing the drag force expression. Okay, so now it's the year of around, let's say, 1800s. Okay, 1800 to 1800, 1900. Okay, so basically, people come up with this new equation of the drag force, and it's according to the Stokes law. Okay, when you hear the name Stokes, then you can think of the equation of the Navier-Stokes equation, right? So basically, it's a set of equations that describes the momentum transfer, the fluid flow of any object, right? So it turns out that if we're just talking about a fluid that's passing by a spherical particle, then this Navier-Stokes equation is going to have an analytical solution. So the Navier-Stokes equation, by default, if you're trying to solve any, for the most of the scenarios, Navier-Stokes equation is not going to have an analytical solution. But if we're just talking about this specific regime, right? So the Reynolds number is smaller than 1, and the flow, and let's say the flow molecules of the flow, the surrounding fluid, is adding a force continuously onto the particle, then under this scenario, there is an analytical solution where we can represent the different force or the flow, the velocity through mathematical equations. So it turns out that the fluid can add two types of forces onto the particle. So one force is just directly onto the surface of the particle. So that's represented in this pressure term, okay? So basically, the force is going to be perpendicular to the surface of the particle. And there's also this shear stress, which is the force that's adding tangentially onto the surface of the particle. Okay, so by integrating these two forces, P plus tau 0, and then over the entire surface area of the particle. Okay, so basically you consider the theta term, right, over the entire range. Okay, so that's theta should equal to 0 to 2 pi, and also the angle that's from the top of the sphere to the bottom of the sphere, that's 0 to pi. And then you can find out that integrating these two terms together, you're going to have a let's say the drag force equals 3 pi mu dp multiplied by Vr. Okay, again, this Vr here is a relative velocity. That's the basically the relative movement or relative velocity between the sphere and the fluid. Okay. Okay, so this is a very elegant equation that basically describes the drag force under the laminar flow region or the creeping flow region. Okay, so we said that, well, the Newton's form actually applies. It's just people don't know what the drag coefficient is at that time. Okay, and the drag coefficient is a strong function of the Reynolds number. So what about we calculate the drag force or the drag coefficient under this creeping flow? Okay, so we can just do that by equating these two different forms of the drag force, which is 1 over 2 rho f Vr squared AP multiplied by CD equals 3 pi mu dP multiplied by Vr. Okay, so we are trying to calculate CD. So first we need to look at the different terms. Okay, so the AP here, what is AP? That's the cross-section area of the particle. So that should be pi over 4 dP squared. Okay, so we can move the terms around. 3 pi mu dP Vr 1 over 2 rho f, and then pi over 4 dP squared, and then Vr squared. Okay, so you can cancel the pi term here, cancel the dP term here, Vr term here. So you are going to have, the 2 will get up, 4 will get up. So that's 24 mu divided by rho f dP multiplied by Vr. So what is this term? So we said that the CD is a function of Reynolds number. So what is Reynolds number? So Reynolds number is just defined as fluid density multiplied by the particle size multiplied by velocity divided by mu. Okay, so you can see this is directly 24 over the Reynolds number. Okay, so this is how the drag coefficient is expressed under the laminar flow regime. Okay, so one thing I need to point out that, well, in the Reynolds number, I don't know if you still can recall what happens in your fluid dynamics class, but basically this mu here is the air dynamic viscosity, right? Or it doesn't limit to air. So this is just dynamic viscosity. Viscosity. Okay, so for the air, specifically for the air, it has a value, under standard condition, it has a value of around 1.9 multiplied by 10 to the minus 5 Newton second per meter squared. So basically, if you think about the transport of the particles in our daily life or in our ambient air, okay, so we are mostly going to deal with particles. If you consider the number, right, most of the particles are going to be smaller than 1 micrometer, which means that the particle size is going to be smaller than 10 to the minus 6. And the fluid density for the air, what is the approximate value? Right? It's around 1 kilogram per meter cubed. Okay? And the velocity is not going to be higher than the velocity of the sound, right? Speed of the sound. So I would say it's most of the time smaller than 10 meter per second. Okay? Especially we're talking about the relative velocity, because the particles have to move against the flow, which makes it more difficult to have a higher velocity. So if you consider all of these, you'll find out that actually the Reynolds number is going to be smaller than 1 for the particles we're dealing with every day, right? So we could assume that all of our particles, that at least for the scope of this work, of scope of this course, we could assume that the particle transport is in the Reynolds, is in the laminar flow or creeping flow condition, so that we can directly use the drag force of 3 pi mu dp multiplied by VR, right? Just this term here. Okay, so basically for the Stokes regime, you can find that there's a specific relationship between the drag coefficient and the Reynolds number, and then if you extend it to the transition region or the turbulent regime, then you can see that under the turbulent regime, for some range of the Reynolds number, the drag coefficient is actually close to a constant, right? So this is probably the region where at Newton's time people were observing. So they're using larger objects, and also they're using a relatively higher speed of the object, right? So that's why you're going to deal with, they are going to observe a relatively constant value of the drag coefficient. But when you get to the smaller particle sizes, then it's going to be a strong function of the Reynolds number. Okay, but for the scope of this class, we're just going to consider the Stokes regime, right, where CD equals 3 pi mu dp multiplied by VR. But there's one thing that people realize later on when we get to the modern time, okay? So if you look at the condition that Stokes assumed, so basically the particle is submerged into a fluid, and then we're assuming that fluid are just traveling along these streamlines, right? So everything's continuous. It's kind of like pulling a soccer ball in the sand, right? The sand are just moving like a fluid. Okay, they don't move around. But what if the particle size is getting smaller? Okay, so we make the particle size smaller and smaller until they're comparable to the gas molecule size. So are the gas molecules still going to follow the streamline along the surface of the particle? No, right? Because now, under this situation, the force is not going to be directly, like continuously adding onto the surface, but the force is going to become the collision, like the random collision onto the particles, right? So even though there are a bunch of gas molecules surrounding the particle, some of the gas molecules will just miss the collision. So this is what people call the slip condition. So basically, under the scenario where the particle size is too small, then the force or the drag force is going to become smaller, right, compared to the continuum regime, because not all the gas molecules are going to add a force onto the particle. Okay, so because of that, people introduce another factor to correct for this, the drag force calculated by the Stokes law. That is 3 pi mu dp multiplied by Vr, and then you divide that by C. So the C here, sometimes, or people will use the CC, is the Cunningham slip correction factor. Okay, so you can think of the extremes. So when the particle size is much, much larger, right, it goes to infinity. Okay, so everything is continuum, right? So then the slip correction factor should equal to 1. But when the particle size is much, much smaller than 1, let's say, or comparable to the size of the gas molecule, right? So the Cunningham slip correction factor should be larger than 1, because basically the force is not going to be continuous, right? So there will be some condition that the gas molecules will miss the collision with the particles. Okay, so it turns out that there is a better parameter that the particle size can compare against. That is the mean free path of the gas molecules. Okay, because eventually it's related to the collision of the it's involving the collision of the gas molecules. Okay, so the mean free path is the average distance traveled by a molecule between collisions with other molecules. So if you can think of the scenario where, let's say, A colliding with B, right? So after A and B just finished their last collision, right? They collided over here, and then C and D collided over here. So you can find out lambda 1, lambda 2, lambda 3, lambda 4. So basically you can calculate an average lambda, or average distance that the molecules travel from their past collision to their current collision, right? So it turns out that the mean free path of the air molecules, let's say if you take a bag of air under the standard condition, the mean free path is around 70 nanometer under room temperature. Okay, so now you can start to find out that when the particle size is much, much larger than lambda, which is around 70 nanometer, right, and we get to 1 micrometer, right? So we can just ignore this slip condition, right? But when the particle size is much, much smaller than the mean free path, okay, we have to consider this slip condition when we consider the transport of the aerosols. Excuse me. So basically, now if you recall the size distributions that I introduced in the last class, what are the general size distributions of aerosols in terms of number? So we introduced the nucleation mode, the Aitken mode, right? And then the accumulation, right? And the coarse mode. So it seems that all of them are not significantly larger than the mean free path, which means that we have to consider the slip correction factor when we calculate the drag force. So then in terms of calculating the Cunningham slip correction factor, people normally use this equation. So C is a function of the particle diameter, which is 1 over 2 lambda dp okay? So basically, it's a function of the mean free path and the particle diameter, okay? So you can see that when the particle size goes to infinity, right, or when the particle size is much larger than the lambda, or let's say the lambda divided by dp is much, much smaller than 1, or let's say the lambda over dp is close to 0, then you can see that basically C, if you plug in this term, right, this term goes to 0, and then also this term goes to positive infinity, but since you have the negative term in front of it, right, so basically the exponential term goes to infinity, no, it goes to 0, right? So because of that, the Cunningham slip correction factor is 1, right? But on the other hand, if you have the particle size much smaller than lambda, so what happens is that first we can look at this term here. So if the particle size is much, much smaller than lambda, then this term goes to 0. Exponential of 0 is 1, right? So basically here you have a constant. And then further, if the particle size is much, much smaller than lambda, then this term will go to infinity. So basically C will become 1 plus 2 lambda dp multiplied by 1.657. And further, since the dp is much, much smaller, which means that the 1 can also be ignored. So basically it means that the Cunningham slip correction factor will become proportional or inversely proportional to particle size. Okay, so you have this relationship here, but you can see that basically this Cunningham slip correction factor is a function of the ratio between the mean free path and the particle diameter. So further, people define this number, the Newton number, which is lambda divided by dp. Okay, so basically, if the dp goes to infinity, Newton number goes to 0. If the dp goes to 0, Newton number is proportional to 1 over dp, right? So basically, the Newton number goes to infinity, I would say. Right? So you have this Newton number proportional to 1 over dp relationship. So if you plot it out, then you are going to see the relationship between the Cunningham slip correction factor or the Newton number as a function of particle size. So as we mentioned, when the particle size is very large, right, they're in the continuum regime, then we don't need to consider the slip correction factor. And that's why for the solid line here, you see when it gets to larger than 1 micrometer, right, the correction factor becomes 1. And when it gets to the smaller particle size, we said that the slip correction factor is proportional to 1 over dp, right? So it has this relationship here. So if you plot it in the log scale, right? So if you plot in the log scale, you can take log on both sides, then they're going to show this linear relationship. So similarly, since Newton number is defined as lambda divided by dp, right? So you're always going to have this linear relationship when you plot in the log scale. And here is further showing you some values of how the Cunningham slip correction factor depends on the particle size. So you can see when the particle size is above 1 micron, right? So when we're talking about dust particles, we're talking about the sea spray aerosols or pollen particles, then their slip correction factor is close to 1. But when we get to the submicron particles, where most of the particles, in terms of number, where they're located, where they're distributed, then we have to consider the Cunningham slip correction factor. Okay, so because of that, then I think it's probably just easier if we just remember that for the drag force expression, we always include the Cunningham slip correction factor because we're dealing with submicron aerosols for most of our time. Okay. So now with the complete form of the drag force, right? So if you recall that when we were trying to solve the particle movement or the droplet movement from the cloud at the beginning, right? We only assume that there's only gravity there. Now with the complete form of the drag force, now we can balance this equation, right? So what we can do is that we can set up the complete differential equation to describe the particle movement due to gravitational settling. Okay, so we're going to set up the Newton's second law. You have the gravity and then the drag force, and then buoyancy can be ignored because the density of the particle is much, much larger than the density of the fluid, right? So that's why we didn't consider buoyancy over there. So then you can have m dv dt equals mg minus fd, right? So which is further mg minus 3 pi mu dp vr divided by c. So here I should note it as vr as well. So then we can, of course, solve this equation analytically, right? Because this is not a complicated differential equation. We're going to do that on the next page. But first, people are interested in what is the final velocity, or people call the terminal velocity of a particle. So the terminal velocity means the final velocity that doesn't change as a function of time anymore. Okay, so if there's no change anymore as a function of time, then the term on the left-hand side will become 0. Okay, so you will directly have mg equals 3 pi mu dp vr divided by c. And further, the mg term, you can assume that the particle is spherical. You have pi over 6 dp to the power of 3 rho p, and then g, right? So you can move the term around. Vr equals dp to the power 2 rho p g c divided by 18 mu. Okay, so we call this as the terminal velocity of a particle due to gravitational settling. Okay, so basically you can see that, well, the terminal velocity is a function of particle size. So in general, the larger the particle size, the faster the terminal velocity. So that's why if you have a like a particle size, assuming that the particle density are the same, right? So if you have a larger particle, then their particle size, if you have a larger particles in terms of size, then their settling velocity will be larger. And especially when you consider the regime where the Cunningham correction factor is close to 1, which means that we're comparing particles of, let's say, 1 micrometer and 10 micrometer, then their settling velocity, let's say VT1 and VT2, is going to have the relationship of the 10 micrometer settles 100 times faster because the particle size plays a, let's say, it has a, we're considering the square of the particle size as a factor in the terminal velocity. But when the, let's say, in the free molecular regime, we know that the Cunningham slip correction factor is proportional 1 over dp. And this means that if you're comparing, let's say, 1 nanometer particle and 10 nanometer particle, then their settling velocity is just going to have a relationship like this, right? Because you cancel one of the dp term in here. Okay, so this is the terminal velocity. So then, as we said, basically for this differential equation, it's not that difficult to solve it analytically, right? And more specifically, you want to understand how the velocity of the particle change as a function of time, right? So we know that if we're considering the free falling of this particle, then at the beginning, you are going to have a velocity of 0, right? And then it's going to increase, and then eventually reach to the terminal velocity. But how fast is this process? Okay, is it going to take like a few seconds, right? If it's, or even, let's say, 1 nanosecond, if it's even shorter, then we can just ignore this initial time and assume that the particles already reached their terminal velocity in the end. Or if it takes years, or it takes hundreds of years, then we can never ignore this initial time, okay? So because of that, we need to calculate how the velocity changes as a function of time. So we need to go back to this equation. Okay, so for this equation here, what we can do is that we can first, now we cannot assume that this term equals 0. So what we need to do is we need to simplify the equation, move the mass term around, and then further we know that the mass is equal to the volume multiplied by the density, right? So we're going to have dVr dt equals g minus 3 pi mu dp vr, and then the mass is pi over 6 dp to the power of 3 rho p, and then multiply by c. So dp term, you can cancel one term here. Pi is canceled, right? So basically this is going to be g minus 18 mu, and then dp squared rho p c multiplied by vr. Okay, so further we can assume this term to be 1 over tau. So you can further find out why we define this term to be something related to time, okay? So you're going to have dVr dt equals g minus vr divided by tau. Okay, so the reason why we define this as tau is also for the unit conservation, right? So the unit here is meter per second divided by second, right? And then we know the acceleration is meter per second squared. And then here, since you have meter per second in the numerator, right? So in the denominator, you should have a unit of second, okay? So then we simplify this differential equation into this equation here by substituting a pretty complex term as a tau. And also you should find out that this term is not changing with time, right? So viscosity, particle diameter, density, and the Cunningham's slip correction factors, they're not time dependent. So they can just be treated as a constant. So now we can further simplify this term or rearrange this term. So you have dv dt equals 1 minus tau, and then g tau minus vr. So we can further substitute this term as a term of, for example, y. Okay, so we know dy is just going to be minus dvr because g and tau are constants. So you're going to have minus dy dt equals 1 over tau y. Okay, so now it's getting more simplified. So you have dy y equals 1 over tau dt. You have a minus sign here, and then you can do the integration. You have log of y equals t over tau, and then you have a minus sign here and plus a constant, right? Because integration, there can be a constant factor there. So then you can find out what's y. So y is just going to be exponential of minus t over tau plus c. But since this is just a constant, you can pull it out because exponential a plus b equals exponential of a multiply exponential of b, right? So it's just a constant, let's say y0, exponential minus t over tau. Okay, so now we can start to substitute the terms back. So basically g tau minus vr equals y0 exponential minus t divided by tau. So how do we find the complete expression? So we know that when time equals 0, vr equals 0, right? Which means that g tau minus 0 equals y0 exponential of 0, which is y0. Okay, so y0 is just d tau. So now if you plug it back in, you're going to have vr equals g tau minus g tau exponential minus t divided by tau. Okay, and you have g tau 1 minus exponential t over tau. Okay, so this is how the velocity of the particle looks like as a function of time when it's doing the free falling. So now if you plot the velocity as a function of time again, so at the beginning it's going to be 0. Okay, So how does it change as a function of time? Is it going to change like this? Or is it going to change like this? Or is it change like this? It's going to change like this, right? Just similar to what we draw over here. So at the beginning, the velocity of the particle is 0, and then it gradually increases until when time goes to infinity, then it reaches to the final or the terminal velocity, right? Which is g tau. Okay, so we can also find out what is the characteristic time for the particle to reach to this terminal velocity. So the characteristic time is just tau. So people also refer this time as the relaxation time. Okay, so the relaxation time, again, if you look at this term here, it's just dp squared rho p c divided by 18 mu. Okay, so this is what we have. So this is, I would say that this term looks quite familiar to us, right? So we remember for the terminal velocity, we had this term, okay? So the terminal velocity, it seems that it's just, the terminal velocity is just g multiplied by the relaxation time, okay? We also show that here. So when time goes to infinity, this term is just g multiplied by tau. So now things are getting connected, right? So basically in a gravitational field, right? You know the gravitational acceleration caused by the gravity. And then the settling or the terminal velocity of the particle is just the relaxation time of the particle multiplied by acceleration, right? So it's also getting more simplified. So as we discussed, this relaxation time really determines what's happening in this initial time for the particle to reach to this final velocity. And it turns out that, well, if you directly look at this equation, the relaxation time is going to be a strong function of particle size. The smaller the particle size, the shorter the relaxation time. So that's why you can see for a particle of around 50 nanometer, which are relatively small in the Aitken mode, they just need around 40 nanoseconds to reach to the terminal velocity, which means that they're really fast in terms of responding to the flow, right? They have a very short relaxation time. And then for the larger particles, like 50 micrometer particles, similar to, let's say, our hair, diameter of the hair, then it needs around 7.7 milliseconds to reach the terminal velocity. Okay, so this is the relaxation time of the particles. You will see the relaxation time later on in the calculation too. Okay, so the next concept is the stopping distance. So when the particles, let's assume that when the particles are being injected into a stagnant airflow, okay, so because the air is stagnant, right, so there at first is going to be a relative velocity, let's say the Vp here. But because of the drag force, it's just going to pull the particle back, right? So there are no other forces, at least horizontally, for the particles. So we can calculate how long does it need for the particles to reach to the stagnant condition, right? So how the velocity changes as a function of time and how far the particles can travel in this stagnant flow. So we can do that by setting up the Newton's second law again. So m dv dt should equal to minus fd, right? So that's minus 3 pi mu dp divided by c multiplied by vr. Okay, again, we should use vr here. Okay, then we divide the m on both sides. So dvr dt equals minus 3 pi mu dp divided by c. And this is pi over 6 dp to the power of 3 rho p vr. So which is further minus 18 mu dp to the power of 2 rho p and then c multiplied by vr. Again, this is our old friend, right? So that's just minus 1 over tau. Okay, so now, I mean, this is an even more simple differential equation compared to this one. So you're directly going to find out that Vr equals v0 exponential of minus t over tau. And further, we know that at time equals 0, it's just the Vp, right, the particle size, the particle initial velocity. So you're going to have Vp exponential minus t over tau. So if you plot the particle velocity out, then it's going to decrease exponentially, right? So when time goes to infinity, it's getting very close to the 0, but it's still not 0 yet. But we can calculate how far the particles can travel when the time goes to infinity, right? So to calculate the distance, it's just 0 integrating to infinity dt, which is Vp exponential minus t over tau dt, right? So further, it's going to be, basically you're going to, so the integral of the exponential term, right, you find out it's tau exponential minus t over tau, right? And so basically it's going to be this term. Okay, let me put it this way. Okay, so basically it's going to be, if you plug in time equals to infinity, this term goes to 0. If you plug in time equals 0, this term goes to 1, right? And then 0 minus 1, and then you have a negative sign here. So then you're going to have directly Vp multiplied by tau. So this is a stopping distance, right? So how far the particle can transport in maximum, right? Because we're integrating from 0 to time equals to infinity. Okay, so although the particle speed is not going to 0, but since the particle speed is decreasing exponentially, okay, so there's a maximum speed that the particles can travel. Okay, so again, the tau here is dp squared rho p c divided by 18 mu. Okay, so you can see for larger particles, they're going to have a larger stopping distance. Basically, this kind of makes sense, right? Larger particles have larger inertia, so if you're trying to shoot a particle in the air, the drag force will try to, their inertia will make them travel longer, right? And smaller particles, their inertia is small, so they cannot travel for far distance. And we can use this mechanism to collect particles. So what we can do is, since the larger particles travel further, we can just put a stage or a wall in front of the flow. So the larger particles, they have longer distances, longer stopping distances, right? For example, if there's no wall here, they should have traveled here, right? So then if you have a stage here, then they will just get collected over here. And for smaller particles, since their stopping distance is shorter, they can just travel with the flow and get away. So this is what people call the impactor. So we can use these impactors and then put them in stages to collect particles of different sizes, right? So for example, here, let's assume it's collecting 10 micrometer particles, and then we can put an enclosure outside the impactor and then make the flow go through another nozzle again, right? Go through another nozzle here, and then we can make the speed larger, right? Basically narrowing the nozzle, so the smaller particles can collide onto the particles. For example, we can set this to be 8 micrometer, and the next stage 6 micrometer, and so on and so forth, and then just measure the mass collected onto the particles, and then further plot the particle mass of each stage, right? 6 to 8, 8 to 10, 10 to 12, and so on and so forth. So then you can get the particle mass-based size distributions, right? So we call this device as the Cascade Impactor. So the next concept we want to cover is the aerosol mobility and drift velocity. So basically, the mobility and drift velocity, these concepts are used when other external forces are used. For example, when there is electrostatic force or magnetic force, basically the particles will move towards a direction that's not caused by the gravity. Okay, so especially on this topic, the the idea or the concept of the electrical mobility. Is quite important. So people use the electrical mobility method to classify particles of different sizes, as I introduced earlier. So people created the scanning mobility particle sizer to measure the particle mobility size and measure their concentrations as a function of mobility size. Okay, so the electrical mobility is defined, or basically people will use the Z, or the letter Z, to represent electrical mobility, is defined as the velocity or the terminal velocity of the particle under electrostatic force or the electric field normalized by the field strength of the electric field. Okay, so now we can calculate what is the terminal velocity, because when particles are just moving within an electric field, let's say this is the field strength, then it has, let's say if we assume that the particles carry positive charges, then it has the electrostatic force of QE, right? And the force that's balancing the QE is drag force, which is 3 pi mu dp divided by c multiplied by VR, right? So, and then since we're talking about terminal velocity, right, so we can just use VT here. So VT is going to be QEC divided by 3 pi mu dp. And then you further normalize it based on the field strength, right? So the E will get canceled. Then you get QC 3 pi mu dp. Okay, and further, the Q is the charges on the particle, right? So you can further find out what is the number of charge, and then you multiply by the elementary charge of a single, let's say, an electron, right? The elementary charge, and then you multiply that by C, the Cunningham slip correction factor, divided by 3 pi mu dp. Okay, so this is how people calculate the electrical mobility. So what happens is that in the instrument that measures the particle size distribution, they can let the particle move within the electric field, and then particles of different sizes are going to have different electrical mobility. So basically, their moving speed or their moving velocity will be different, right? So based on the velocity, you can separate them out and then find out what are the concentrations of particles with specific electrical mobility and further convert it into the particle mobility size. Okay, and similarly, the drift velocity is defined, it's just the terminal velocity. So the drift velocity is just the terminal velocity under the specific external force. It can be electrostatic force, magnetic force, or the thermophoretic force. Okay, so the next concept is the particle Brownian motion. So here I have a short video that you can look into. So the particle Brownian motion is just when the particle sizes are becoming smaller, then since the particles are in the surrounding air, right? So the air molecules are going to collide with the particles. And then since the size is comparable, and then the particles and the air molecules are not continuum, right? So you're going to have some scenarios that there may be more particles hitting the particle, more air molecules hitting the particle in this direction, and then the next time the particles may be moving this direction. So overall, the particles are going to have a random motion, and we call this random motion as the Brownian motion. Okay, so here is the short video. So the video is demonstrating.
Okay, you can see Liam here. He has set some corrugated cardboard on fire.
So the video is demonstrating how the smoke particles move in a stagnant cell, air enclosure. Okay, so then this person uses a magnifier to look at how the smoke particles move around, like randomly.
And he's using a dropper to suck some of the smoke up that comes as part of the smoke cell. And shortly he'll place a cover slip over the top of that. He's placed a little bit of Vaseline around the top of that glass reservoir to make a seal between it and the cover slip, keep the smoke inside. He's using the lowest powered magnification on a simple microscope here. And this is the image that's seen through my iPhone camera. So we're seeing here something like about times 40 times 50. And what you're seeing are particles of soot reflected in the light. The particles of soot made up of carbon are just big enough to see under this magnification. We cannot see the particles of air, but we can see what the air particles are doing. They're whizzing about, bumping into the particles of soot and jostling them. And particles of soot then are moving in a random manner. That's the smoke cell.
Okay, so as you can see, the particles are basically moving randomly because of the Brownian motion and because of this collision of the surrounding air molecules. So then people are interested in, well, how far can these particles travel because of this random motion? So because this random motion also, I mean, in terms of direction, it can be in any direction, right? So there isn't a, if you basically average all of the displacement of the particles make, it can be in all different directions, right? And it can also be in all different distances. So if you plot their displacement, okay, as a function of their frequency, basically the number of particles making this displacement, then you are going to show a Gaussian distribution. Okay, so further we can calculate what is the magnitude, basically what is the average distance of the particles traveled, right? You can see most of the particles are going to make no distance no distance, right? So which means that the particles are like randomly moving around, and then most of the particles will get back to its original location. Okay, but there are maybe some particles that can travel further. So overall, if we want to calculate what is the average distance, like what is the average displacement, or the magnitude of the displacement, then you can use this equation here, where basically the average magnitude of the displacement compared to the original location is just going to be the square root of 2 dt. And t here is time. It can be seconds or minutes or hours or even years, right? And then the d here is the diffusion coefficient, basically this term here. Okay, so then you may have the question, how do we calculate the diffusion coefficient specifically of a particle, right? So according to the Stokes-Einstein's equation, the diffusion coefficient of a particle in the air can be calculated by kT divided by F. Okay, so the K here is the Boltzmann's constant. Okay, T here is the temperature in Kelvin, and then F is the friction factor. Okay, so basically the friction factor is just the drag force divided by the velocity. Okay, so if you recall, the friction factor is, the drag force is 3 pi mu dp divided by c multiplied by VR, and then you normalize it by VR, so you have 3 pi mu dp divided by c. Okay, so this is a friction factor, and if you plug it in, the diffusion coefficient is going to be KTC divided by 3 pi mu dp. So as we introduced earlier, right, so if you are in the continuum regime where the C is close to 1, you can see that D is proportional to 1 over dp. And then when you get to the free molecular regime, when the particle size is very small compared to the mean free path, then C is proportional to 1 over dp, right? So this is going to be D proportional to 1 over dp squared. So basically, it means that when it gets to this even smaller particles, the particles are becoming more diffusive until their size is comparable to the gas molecules, right? If their size is compared to the gas molecules, they're just going to move through random motion, collision, having the mean free path, behaving like a gas molecule, okay? So this is how we can calculate the diffusion coefficient of a particle. And in general, the diffusion coefficient of a particle is smaller compared to the gas molecule, okay? And it also has a unit of meter squared per second, okay? So D is carrying a unit of meter squared per second. Okay, so basically these are the aerosol single particle dynamics I wanted to introduce. And then at the end of this class, I wanted to basically go back to the original question about the selection of tubing materials. Okay, so if you want to set up a system and then you want to set up a particle sampling lines, or basically use these different types of tubings. So to sample these aerosols, you want to avoid the loss as much as possible. For example, if you want to analyze 1 nanometer particles, right? So new particle formation is a pretty important topic right now to try to understand where the particles are coming from, right? So if you want to measure 1 nanometer particles, then you need to understand what is the diffusion coefficient of the particles. You don't want the particles to diffuse to the wall, and when you measure it, you don't have much particles left, right? So the diffusion is going to play a role in the particle sampling. But at the same time, if you want to measure the dust particles, then you want to avoid these bends here, right? So if you recall, for the impaction, it's basically the bending of the airflow. And the larger particles, they cannot, because of the longer the stopping distance, they cannot make the sufficient bend to avoid the obstacle here, right? So you want to avoid the inertial deposition. And at the same time, when you are trying to sample the particles, right? So there's sampling the particle and also transporting the particles. So when you're sampling the particles, you don't want the airflow to be introduced to the tube in an angle, right? If there's an angle, then you still have the impaction or basically inertial deposition of these particles. And also you want to match the flow that your instrument needs, and also the velocity of the surrounding flow, right? For example, if the outside air has a speed of 10 meter per second, then you want to match the sampling velocity to be also 10 meter per second. So the reason is if this speed is too low, let's say 1 meter per second, okay, so most of the flow will get diverted back, right? And under this situation, you are oversampling the larger particles because their inertia is larger, right? They can just get introduced to the tube. And then the smaller particles are not basically undersampled, right? So undermeasured. So these are the concerns we need to consider when we're sampling the aerosols into our instruments. We're going to get back to this topic probably in the next class or 2 classes later. Okay, so that's it for this class, and feel free to let me know if you have any questions.